We now come to optimization problems. So the general form for optimization problems is as follows. We write that x star is equal to arg min of f naught of x, fi of x, so subject to fi of x less than equal to 0, hi of x equal to 0. We have already seen this form before. If you remember, we called this as the objective function, and these as the inequality constraints, and these as the equality constraints. Here x star is the optimum, and the optimization is with respect to x, which is called the optimization variable. So x could be a vector, it could be a matrix, for instance. So what is missing from here? You can observe that even for us to write down this problem, it is necessary that x should belong to domain of f naught. In fact, it should also belong to domain of fi and also to domain of hi. So this constitutes the so-called implicit constraints. Implicit because they are often not written as such. These are the explicit constraints, but there is also implicit constraints which say that x should belong to the domain set, which is defined as the domain of f naught intersection with, let's say, from I equal to 1 to m, domain of fi, and then this is intersection with I equal to 1 to p, domain of hi. Right, so these are all the domains of various functions, and we definitely want x to belong to this domain set for us to even substitute x and check whether these are satisfied or not. So for these functions to be well defined, it is necessary that x should belong to the domain. So we will generally only write as this if we want to emphasize the implicit constraints. Usually we may not even write down the implicit constraints. So let's take a simple example. Let's consider the example minimize over x. This is a vector x in Rn, C transpose x minus summation over I from 1 to m log of Ai transpose x minus Bi. Right, so observe here that there are no explicit constraints, there are no inequalities or equalities like in this problem, but instead we only have domain restriction that x should belong to the domain of the objective function. So what is the domain of the objective function? So domain of f naught in this case is, so we require this should be the set of all x such that this logarithm is well defined. Remember that things are in real space here, and the objective must always be a real number. So we require therefore that Ai transpose x minus Bi is greater than 0. So this is the domain, and we therefore want x to be in the domain, and this should hold for all I from 1 to m. So this is the domain restriction, and whenever you are looking at any problem, you have to be careful that it may be associated with some implicit constraints arising from the domain of various functions. So here x star is the optimum solution. There is also a possibility of having a feasible solution. So a feasible solution is x tilde if it satisfies that x tilde is in the domain, first of all. So x tilde is feasible if it is in the domain, and fi of x tilde is less than equal to 0 for I equal to 1 to m, and hi of x tilde is equal to 0 for I equal to 1 to p. So in other words, x tilde is feasible if it satisfies all the constraints. Doesn't matter what it is at the objective. Next, observe that f naught of x star. So x star, remember, was the optimum value. F naught of x star can also be written as minimum of f naught of x subject to all those constraints, fi of x less than equal to 0 and hi of x equal to 0. So this is for I equal to 1 to m. This is for I equal to 1 to p. So this is f naught of x star. Now, if you remember, we said earlier that in this context of convex optimization, we will often define values over the extended real line. So in this case also, we can define f naught of x star as taking values over the extended real line, which means taking values including infinity and minus infinity. So we define it like this. We say that this is finite if the problem is solvable, right? So if this is solvable, then it is finite. But there are other scenarios where the problem may not be solvable. For instance, there is a possibility that the optimum solution is unbounded below. If the optimum solution is unbounded below, which means that you can take f naught of x to be minus infinity, then we define it as minus infinity. You can take it as small as possible, then we define it to be minus infinity. And finally, we define it to be infinity if the problem is infeasible. In other words, there is no x tilde which satisfies the constraints, and therefore there is no question of finding the optimum. So these are the two additional definitions we have defined, and you will actually observe that these will be very useful later on when we consider duality. Let's take a simple example to consider when the problem can be unbounded below. The infeasible case, I hope it is simple to understand. If there is no possibility of finding a solution which satisfies fi of x less than equal to 0 for all I, then it is an infeasible problem. So when would a problem be unbounded below? Let's consider a simple example. Let's say we are saying that minimize ai of xi, I equal to 1 to n. So this is x in Rn, and we have the constraint that xi is greater than equal to 0 for I equal to 1 to m. So what are the various possibilities for this problem? First of all, this problem is always feasible, so the solution will never be infinity. So the minimum value of this will never be infinity, but it can be finite or it can be minus infinity. So observe that in this case, the solution is 0 if ai is greater than equal to 0 for all I. Right? So the solution is 0 when ai is greater than equal to 0 for all I. Why is that the case? Because we have xi greater than equal to 0 and we are minimizing ai xi. So if all the ai's are positive or non-negative, then this is a non-negative weighted sum of non-negative numbers. So this value, this objective function in that case would always be greater than equal to 0. And in fact, it would attain the value 0 if I take all the xi's to be 0. So in this case, x star would be 0. On the other hand, what would happen if one of the ai's, let's say a1, is less than 0 while a2 to an are all greater than equal to 0? What happens if one of the ai's is less than 0? So even if one of the ai's is less than 0, what would happen is we can take that x1. So let's say in this case it would be written as a1 x1 plus a2 x2 and so on till an xn. So what can happen in this case is that I don't care about these, so I take x2 to xn to be 0, right? So I don't care about these, and in fact these terms will be minimized for by taking x2 to xn to be 0 as in the first case. But how do we minimize a1 x1 for x1 greater than equal to 0 and a1 negative? You can see that if I take x1 to infinity, then this goes to minus infinity, right? As I take larger and larger values of x1, the objective function becomes smaller and smaller. And in fact, as per our definition, this is an unbounded below problem, because the objective function is unbounded below whenever a1 is less than 0. So for a1 less than 0 case, we have the objective function, the minimum of the objective function defined as minus infinity. So this is an example where the objective function could be minus infinity. Of course, it could be minus infinity when two of the AIs are less than 0, or many of the AIs are less than 0. So even if one AI is less than 0, then it is minus infinity or unbounded below. There is also a special type of problem called the feasibility problem. So feasibility problem is one where we just want to find an x such that all the constraints are satisfied. Right? So this is a feasibility problem. Another way to write this problem is to write at minimize 0 subject to fi of x less than equal to 0, hi of x equal to 0. So it's just another way of writing it, or you can think of it as another notation. Note that the possible values this can take is 0 if this is a feasible problem. So if a feasible solution exists, but it would be infinity if not. So if this problem has no solution, then we could say that the problem minimum value is infinity because it is a infeasible problem. So remember, in the infeasible case, we were defining the objective function to be infinity. So that's what also happens in the feasibility problem. So we have seen the standard form for the optimization problem, and we have defined some notation surrounding it, and also some aspects of implicit constraints and feasible solution. One thing to notice is that any problem can be put into this form. So any optimization problem can be written in this way. For instance, consider the problem with box constraints. So we have, let's say, a problem of this form where xi is between li and ui. Now this constraint may not look like it is in the standard form, but you can always write this problem as minimize f naught of x such that xi minus ui is less than equal to 0 and li minus xi is less than equal to 0. So this holds for I equal to 1 to n, and this also for I equal to 1 to n. Here actually p is 0, there are no equality constraints. So this is an example where we have converted a problem into the standard form, even though it was not originally expressed in this form.